Have you ever stared at a scatter plot, just a messy cloud of data points and thought, how in the world do I find the one single line that actually makes sense of all this? Well, that's exactly what we're going to tackle. We're diving into Least-Squares Regression, which is just a fancy mathematical way of finding the absolute best fit line for your data.
So, here's our game plan. First, we'll nail down the big idea. What is a best fit line? Then, we're going to crack open the equation that actually builds it. After that, we'll figure out what those numbers in the equation really mean in the real world. From there, we'll actually use it to make some predictions. And finally, we'll ask the most important question of all. How do we know if our predictions are any good?
All right, let's get right into it. What exactly is this best fit line? And how does it help us find the real trend that's hiding inside a bunch of noisy data?
Okay, picture it, a scatter plot. Maybe it's hours you studied versus your exam score. You could just eyeball it, right? Draw a line that looks pretty good. But your pretty good might be different from mine. So how do we find the one line that is mathematically, without a doubt, the best one? What does best even mean here?
Well, the answer is the least squares regression line. I know, it's a mouthful, but the idea behind it is actually pretty genius. It's the one and only line that makes the total amount of prediction error as small as it can possibly be. And the trick is how it does it. It looks at the error for every single point, squares those errors, and then adds them all up. We square them so that positive errors and negative errors don't just cancel each other out. It also means that big misses get penalized way more than small ones. It's really the ultimate definition of a best fit.
So we know what the line is supposed to do, but how do we actually, write it down? Every line has an equation, and this one's no different. So let's decode the formula that's running the whole show.
And here it is. Look familiar? If you remember y equals mx plus b from your algebra class, you're pretty much already home. This little equation is our powerhouse. That little hat on the y, we call that y hat, and it just means it's our predicted value. The b0 is our y-intercept, think of it as our starting point, and b1, that's the slope, that's the engine of the whole thing.
Now, this right here, this is probably the most important distinction to get straight. Y hat is what our line predicts. It's the model's best guess. But y, with no hat, is the real deal. It's the actual data point we saw in the real world. And the gap, the distance between what the line says and what really happened, that's our prediction error, and it is everything.
Okay, knowing the parts of the equation is one thing, but the real magic happens when you can translate those numbers into something meaningful about the world.
Let's start with the slope, b1. This tells us, on average, exactly how much we expect our outcome, y, to change every time our input, x, goes up by one single unit. Is the relationship going up or down? Is it a steep climb or a gentle slope? The slope tells you all of that.
Let's make this super concrete. Say we built a model to predict salary from years of education, and our slope came out to be 4,200. The interpretation is just this simple. For every one additional year of education someone gets, we predict their salary will go up by $4,200 on average. See? It's not just some random number. It's a clear, powerful statement.
Next up is the y-intercept, b0. This is our baseline. It's what the model predicts for y when our input variable, x, is all the way down at 0. It's literally where our line hits the y-axis.
But wait a second. You have to be really careful with the intercept. It doesn't always make sense in the real world. You got to ask yourself two questions. First, does an x value of 0 even make sense for what you're studying? Like, if you're predicting weight based on height, a height of 0 inches is meaningless, right? But if you're predicting a test score based on hours studied, 0 hours is totally possible. And second, is x equals 0 even anywhere close to the data you actually collected? If you studied students who all studied between 10 and 20 hours, then the intercepted 0 hours is just a wild guess way outside your data.
Okay, so we've got a handle on what the slope and intercept mean. Now it's time for the fun part, putting this thing to work and doing what it was made for, making predictions.
And honestly, this part couldn't be easier. Once you have your equation, you just take the x value you're curious about, plug it in, do the math, and boom, out pops your predicted y hat. So here, if our x is 16, our model predicts a y value of 92.2. Simple as that. But, and this is a huge but, this power comes with a giant warning label. There's a super common and really dangerous trap called extrapolation. It's what happens when you get cocky and try to make predictions for x values that are way outside the range of the data you actually have.
So here's the bottom line.
Making predictions inside the range of your data, that's called interpolation, is generally safe. But trying to predict far outside that range, extrapolating, is super risky. Why? Because you have zero evidence that the trend you found actually continues. The relationship could totally change, and your model would be flying blind.
Which brings us to our final and maybe most important question. We made a prediction, but looking back at our actual data, just how good was our guess? How far off were we?
We measure this with a really neat tool called a residual. A residual is just the leftover error. You just take the actual value, what really happened, and subtract the predicted value, which your model guessed. It's the gap between reality and the prediction, for one single point.
Let's walk through one real quick. Imagine our model is y hat equals 5 plus 2x, and we know there's a real data point at x equals 4, y equals 15. So first step, we plug our x value of 4 into the model to see what it would have predicted, and it looks like it predicts a value of 13.
All right, now for part 2. We take the actual value, which was 15, and we subtract our model's prediction, which was 13. The answer is a positive 2. That number, positive 2, is our residual. It tells us exactly how far off we were for that one point.
And the sign of that number is super important. A positive residual, like the plus 2 we just got, means the actual value was higher than what we predicted. Our model underestimated. A negative residual means the opposite. The actual value was lower than our prediction, so our model overestimated.
And that kind of brings us to the final big idea. We know how to find the best line, we know what all its parts mean, and we know how to measure the error for any single point. But how do we grade the model as a whole? How do we put a number on how good our line is overall? That's the crucial next step on your journey with statistics.